So it's finally time to go down the rabbit hole of parahydrogen and what that means for NMR. The whole course so far has really been building towards understanding and explaining this. We talked about spin states and superpositions. We talked about how to resolve those superpositions when you do a measurement on them. We also talked about energy and then spin states and NMR, and it all ends here. It all really accumulates together. So if you can follow everything up to now, this will start making a lot of sense. So we need to talk about the spin isomers of hydrogen, and then how to create something called parahydrogen. And then once we can make that, what can it do for NMR? What can it improve? What problems does NMR have, and how do we fix it? So let's recap. These are the four spin states in hydrogen. We have our down beta one, the up or alpha one, and then in the middle two linear combinations. They are the superpositions of the two states that don't really work. Up and down up don't work when the molecule is symmetrical. So I'm going to quickly do something. I'm going to label these by which spin they're on, either 1 or 2. So the beta here is on 1, the beta here is on 2. What we can do is do something called permutational symmetry. We can exchange these labels, and let's go ahead and do that. They just swap around. So all we've done now is swapped labels around. Now we're going to rearrange this and put it back in the original order that it had. And then, if you notice something, one of these is slightly different now. What we've done is a symmetry operation, just the same ways that you'll see in group theory. We've just permutated it to see what happens, and one of them has come out negative. So these have remained positive, these have remained positive, these have remained positive. That has become negative. We refer to that as anti-symmetric. It is anti-symmetric with respect to label exchange or permutational symmetry. The other ones are symmetric. That gives us two different categories of spin state, the symmetric and the anti-symmetric one. This has a consequence on the overall wave function of hydrogen. So H2, that molecule, has a wave function that's combined with the electronic function, the vibrational, the rotational, and its spin state. So everything there is all related, and it must be anti-symmetric overall. We can't really do much about the electronic or the vibrational functions right now, but the rotational and the spin ones are interesting because that spin state there can be symmetric or anti-symmetric, and so can the rotational state. And if we change one, the other's got to change as well. So let's show you what that means. The anti-symmetric spin state is that one we picked out when we did the permutational symmetry to it. This here, that is the antiphase linear combination. They are subtracting to make that superposition. That is only compatible with the symmetric spin states. This is really interesting. The nuclear spin state is affecting the rotation of the molecule. So the molecule can only rotate with certain amounts of angular momentum depending on what the spin state is. So we picked up in spectroscopy, particularly rotational spectroscopy, that we must have J values of 0, 1, 2, and so on. Well, the symmetric rotational energy levels are 0, 2, 4, and 6, etc. All the even number ones, including 0. The anti-symmetric rotational levels are 1, 3, 5, 7. All the odd numbers, they are anti-symmetric. So if the molecule is in any one of those numbers, it can only have one of these 3 spin states. Only one of those. Whereas if it's in the symmetric rotational state, it's restricted to the anti-symmetric spin state. That's interesting because it means we can now pick which spin state of hydrogen we want based on its rotation. So this gives us two kind of manifolds or two isomers or spin isomers of hydrogen. We have parahydrogen and we have orthohydrogen. This also makes sense if we talk about the spin angular momentum as well. This has an overall spin of 0. This has an overall spin of 1. Basically, because we're adding spins, we're adding a half, and plusing a half, and subtracting a half. Here we have plus a half and plus a half, which equals 1. So if you've done any of the terms and states where you're adding spin numbers together, that will look familiar to you. And then similarly to orbital angular momentum, well, if this spin is 0, then there's no way we can orientate it. ms must be 0. Here, however, ms can be either plus 1, 0, or minus 1. So we have basically plus 1, minus 1, and 0 here. So those equations are also associated with angular momentum being distributed in a particular direction. So the consequence of this is that cold liquid hydrogen will mostly be in one spin state, predominantly parahydrogen, because J equals 0 and J equals 1 are separated by about 1 kilojoule per mole. That's a minuscule amount of energy, so at room temperature they're about equally populated, and when it comes to the spin isomers, they are about in a 1:3 ratio thanks to the degeneracy. So all 4 of those spin states are populated equally, or in about a 1:3 ratio of para to ortho hydrogen. But if we cool it down, we can get everything into the J equals 0 state and only parahydrogen. That has an interesting consequence if you're dealing with a lot of hydrogen, for instance, because if you remember this thing, that big orange fuel tank there is filled with very cold liquid hydrogen. And it's not necessarily parahydrogen either, it could be a mixture, because it's a spin forbidden process, it needs catalyzed. If it suddenly happens, if it drops from J equals 1 to J equals 0 inside there, it releases energy. And 1 kilojoule per mole doesn't sound like a lot when you're dealing with a small lab quantity of hydrogen, but when you're dealing with a giant fuel tank of liquid hydrogen, that's a lot of energy. That is enough energy to boil that hydrogen off catastrophically. Basically, the transition from orthohydrogen to parahydrogen could cause that fuel tank to explode. So this is very deliberate. They pass it over a paramagnetic catalyst to turn it into parahydrogen first. The fuel tank there is very specifically filled with parahydrogen. I'll put an additional link in the advanced information to someone's thesis in mechanical engineering about this, because it's really interesting. If you want to minimize your boil off in space, you've got to make sure you're using parahydrogen, not orthohydrogen. Otherwise, that transition from J equals 1 to J equals 0 could cause your hydrogen to boil off. So it's a real effect. The numbers and the amount of energy here is really quite important on a large scale. So how are we going to make parahydrogen? Well, we just cool it down in the presence of a catalyst. At room temperature, we've got that 1:3 ratio of para to ortho. If we chill it down in front of a catalyst, everything's going to become parahydrogen. At about liquid nitrogen temperatures, that's about 77 Kelvin, it's about 50-50. At about 10 Kelvin, it's about liquid helium temperatures, a few degrees above absolute zero. It's about 99.8% or so parahydrogen. So this is a really enriched mixture of one spin isomer and very little of the other. And because it's a spin forbidden transition, when we warm it up in the absence of a catalyst, it persists. We keep parahydrogen there. So we can get a room temperature sample of pure parahydrogen and no orthohydrogen. We have selectively populated and can keep one of the spin states and not the other. So what's the point of all of that? What is parahydrogen? What's it got to do with NMR? Well, NMR is great, but it has a few drawbacks. First of all, the signal intensity on NMR is very low. If you deal with mass spec, you can use minuscule amounts of your product. If you're using any other form of spectroscopy, you can use any amount of product you like. You will still mostly be able to get a spectrum out of it. NMR, not so. It requires huge amounts of material compared to others. So this requires dozens or even hundreds of separate scans. Usually if you're in a lab and you take an infrared, it'll scan anywhere between 4 and 16 times. NMR, you need 16, 32, 128, 256. Just, it keeps going up. You need lots and lots of scans. And the downside to that is things like MRI scans, if you're going to go for a brain scan or a diagnostic scan of any part of your body, that can take 20 minutes to an hour. fMRI, that happens almost in real time, can only work because it's super low resolution. If you want to diagnose someone and really have a good look inside their body, you need them in an MRI scanner for 20 minutes, 40 minutes, an hour. And if you want to do a complicated NMR spectrum, you want to acquire something more than protons. You want to do carbon-13 without enriching it. You want to do a rhodium spectrum. You're booking out your spectrometer over the weekend. It needs days to run. So NMR has a problem. Its signal intensity is very, very weak. So let's kind of explain this with a chemical example. So this molecule here is known as Vasquez complex, and it is the prototypical catalyst. It's been known since the 70s, and it's a really interesting one because if you react it with hydrogen, H2, it breaks hydrogen apart. It will do this quantitatively as well. All the hydrogen that you put over the catalyst will break into 2H here. So this is like a 100% yielding reaction. Really interesting. So that can form the basis of a lot of catalysts that require hydrogen. So what we're doing here with the hydrogen is we are going from one set of spin states to another. Here we have the symmetrical spin states in H2. Here we have the asymmetrical spin states in the complex. Let's put the metal thing in there. So we are going from one set of symmetry conditions to the other. We are breaking the symmetry of hydrogen. And what happens? Well, we changed the allowable spin states, haven't we? So here we have beta beta. That is populated in hydrogen. That is going to populate that energy level there. Alpha alpha, that is going to go populate that energy level there. Now the superpositions. Remember, we're talking about resolving superpositions. Well, these coefficients here, when we square them, give us probability. 1 over root 2 squared is half. So half of the molecules in this spin state will populate to here, half will populate to there. And the same is true for this one. Half will go there, half will go there. The end result of that is that all of those spin states in the molecule are equally populated. And that's why NMR has a really low signal intensity. Each of those populations reduce the signal intensity. If you fire photons at this, the equivalent of 1 in 30,000 nuclei actually absorb a photon. It's a really inefficient process. That's why we need to scan NMR for a long time. We need to do it again and again and again to build up some signal. What happens if we do this with just parahydrogen though? We have cooled hydrogen down, we put it into a single spin state. We don't have any of the others there. What's going to happen when this reaction occurs? So providing the reaction happens in a concerted fashion and the spin states are preserved, well, we can't populate that. That would require flipping a spin, which can't happen. Definitely can't populate there either. It will require flipping a spin. All we can do is populate that state and that state. So we have a 50-50 chance of resolving it there, or a 50-50% chance of resolving it into that state. The end result is that there is now a not very even population of these spins, usually represented on these diagrams by making some of the lines a bit fatter. So we're now seeing that there is a lot more spins on those energy levels compared to the other two. And the consequence of that is that these transitions become a lot stronger. Another interesting consequence is that these two transitions at the bottom become emission. We no longer have molecules going in that direction. We don't have the spin states going up. They are all now in emission and stronger. So let's look at Vasquez complex again. in NMR. We have a hydrogen atom and a hydrogen atom. They're going to couple together. One's opposite CO, the other's opposite Cl. So they are in different chemical environments, so they're going to have different chemical shifts. They couple to each other to form doublets. So you get something like this, 2 doublets out, which we've seen before. The real spectra, they couple to phosphorus, so they're actually doublets of triplets or triplets of doublets, whichever way around you want. But we can hand wave that away for now. The spectrometers can actually saturate that out and just get us the doublets. But if we took an NMR spectrum of Vasquez complex, we end up with something like this. If we do it with parahydrogen, though, it changes significantly. Now we've got 2 things that are happening. One, we've got these antiphase signals. One is in emission, one's in absorption, and they're much bigger. They are hundreds, if not even thousands of times, I think up to a theoretical maximum of about 30,000 times stronger than before. So previously, what took hundreds of scans can be done in a single scan. We can get a spectrum like that out immediately. So actually, let's look at the real thing here. That's the actual real NMR spectrum. So you can see the antiphase signals here. You can see this one's also antiphase. We've got that phosphorus coupling in there, so it's actually a triplet of antiphase doublets, but you can see some pointing up, some pointing down, and they're much more intense than previously seen. So much more intense, in fact, that we can begin to see these signals via NMR. And that is due to that isomer there. Previously undetected, we didn't know that H2 could actually add in that way. So instead of the phosphoruses being axial and opposite each other, they've actually bent back and become cis to each other. So we're now seeing that, and we can characterize it by NMR by using parahydrogen, because the signal intensity is now hundreds of times higher. We would previously need to maybe scan it tens of thousands of times over days to see something like that in solution, by which point your catalyst may have well broken down or there's oxygen in there. So now parahydrogen is showing these things. And if that was a reaction intermediate, we'd be able to see it. Normally they would have concentrations of 0.01%. Now we can see it. Let's do another couple of examples. This, actually one of mine, this is a rhodium dimer. So this molecule, all we've done is swapped iridium for rhodium, doesn't add H2. It's previously thought to be inactive, but you add parahydrogen to it, you can begin seeing these molecules. That's very similar to how Vasquez complex works, but because it's in such a low intensity, or such a low concentration, it begins to dimerize with the original here. It loses carbonyls. So what we've got here is actually 2 isomers, one there and one here. And you can kind of see there's actually more couplings in there. That's it, coupling to rhodium. 103, rhodium is NMR active. Its spin is equal to a half. So it's a really nice metal to play with in NMR. It's NMR active, unlike iridium, so you can see it and characterize more complicated molecules using it. And we couldn't see this without parahydrogen. It would take days to see. And that's assuming it was stable and would last long enough as well. So we can see this within maybe a minute of scanning or a single scan. And then finally, this is a different technique. It's related, but it's not one. I will dump it in the wider reading below, but this is applying the same thing to MRI. So the image on the left, that's a NMR tube filled with capillary tubes. So what we can see here are tiny little capillary tubes inserted inside an NMR tube, and there's hyperpolarized pyridine around it. That pyridine now has that weird distribution that comes from parahydrogen rather than just the thermal Boltzmann distribution. And that is now super bright. So that is a very thin slice through this tube, and we can see it really brightly. Here, it's actually a much thicker slice. The spectrometer is looking at that much rather than a tiny slither of it. And it's scanned for 160 times. It's doing it 160 times longer, and you can barely see it. So that's trying to pick up pyridine via NMR, but suddenly we're mixing parahydrogen in there and it glows brightly. In fact, it's so bright, that one scan is not only enough, it's actually too much. an engineer had to come out and rebuild the amplifier on the NMR spectrometer in order to attenuate that image down so you could see it properly. It was otherwise the image was too bright. That's practically glowing in the NMR tube. And that's the power of making these non-Boltzmann, non-equilibrium spin states. If we selectively populate them, we can generate much better NMR images. So let's briefly recap what we're doing. H2, the hydrogen molecule, has two spin isomers. Call them parahydrogen and orthohydrogen. And we can selectively create the parahydrogen one by cooling it down over a catalyst. Parahydrogen's more stable, it's more energetically favorable by a very tiny amount of energy, 1 kilojoule per mole-ish. But if we chill it down to liquid helium temperatures, a few degrees below absolute zero, the proportion of that shoots up a lot. Now, if only parahydrogen reacts with something, we can selectively populate or selectively synthesize a spin state in the product. And that produces a higher signal intensity in NMR. Our number of scans go down from the hundreds and thousands to just one. And we can go down from days and hours to make a scan to mere seconds.